This is our NASA Mars Lander final report for first year engineering lab section 6 for spring of 2026, and our company name is Planet X Co. For an overview, we are starting with the introductions and background, and then we're going into the requirements for the project, our final design, and then how the manufacturing activity went, test results, and finally the conclusion.
I'm Samuel Farson, and I'm the construction manager.
I'm Mila Walsh, and I'm the project manager.
And I'm Enrico Thomas, the test engineer.
So this is our background request for proposals, or the RFP, and it basically goes over what our project guidelines are, and some important points include that we're using two pilots, which are eggs, and that we're performing the test twice, so our vehicle must be reusable. So our customer requirements are that the Mars lander shall deliver astronauts to the surface of Mars. The Mars lander performance shall be demonstrated during video recorded tests on launch day. The Mars lander shall carry two pilots, which are eggs, and the Mars lander should be reusable. And then our contract requirements are that the Mars lander shall deliver astronauts to the surface of Mars. The demonstration vehicle shall be built in 30 minutes. The demonstration vehicle must land on tile. The demonstration vehicle must be comprised of recyclable parts. The demonstration vehicle must be reusable, protecting the eggs twice total, with a potential third endurance trial if the two first trials are successful. The demonstration vehicle must survive an 11-foot drop twice and may survive a 30-foot drop once for our endurance trial. And the demonstration vehicle must cost no more than the budget offered, which is $15.
So this is a drawing of the final design we kind of decided on. In the top right, you can see the isometric view of the box, where as you can see, the box is quite literally a cube, which is it's 0.67 feet on each side, which is about 7.2 inches. On the top view, you'll see two squares on either side. These are the socks that the eggs are in. These are made out of bubble wrap. And in the front view, you can see how these socks are kind of nested onto actually an inflated bag for cushioning. In the bottom right and left, and actually all the corners, you can see that there's crumpled up pieces of paper. These papers kind of lift the sides of the bags up so the sock in the middle can go farther down into the box and be covered on all sides by the bag. Then at the top, you can see that there's another Walmart bag that's completely inflated to prevent any ricocheting off the top whenever it lands on the ground. At the side view, you can kind of see how the compartments work, where there's two pilots, so they each get their own room. For the materials that we used all $15, and we spent $5 on one piece of cardboard that was 2 foot by 2 foot, $1 on 10 sheets of copy paper, $8 on four pieces of 1 square foot sheets of bubble wrap, and $1 on four Walmart grocery bags. This is a visual representation of all the materials we used and our team number. We were team 8. For the construction plan, there is about 15 different steps total. Step 1 is that we measured the piece of cardboard and marked where it should be bent in order to form the box. Step 2 is we folded the cardboard piece into a box, ensuring that the sides are even and that the box has enough material to close. We then taped the corners together. Step 3 is that we tied the Walmart bags, and we ensured that there was ample air inside the Walmart bags so it could protect the eggs. Step 4 was practice fitting the eggs in the bags to kind of get a feel of how the inside of the box were going to kind of play out, how much space we would have, and see how much extra space was remaining in the box. Step 5 is we would remove the eggs and bags from the box and then tape the openings of each bag shut to ensure that no further air escapes. Step 7 was that we wrapped each egg in bubble wrap to secure the egg once it's fully surrounded. Step 8 is we would wrap all interior walls, including the bottom and the top, in bubble wrap and secure with tape. Step 9 is to place the bags and eggs back into the cardboard box, ensuring that the bags are properly surrounded by the eggs or surrounding the eggs. And this is again to get the final feel of the spacing inside the box. Step 10 is fill in any free space with crumpled up sheets of copy paper, which we ended up just using in the corners. Step 11 is if there's any empty space, use the rest of the bubble wrap. But at this point, we didn't have any bubble wrap left. Step 12 close the box and secure the opening with tape. And step 13, we would practice shaking and flipping the box to kind of simulate these test trials. So there were some changes in the plan that were made and improvised in the moment. These include that instead of folding a six-sided box from a 2 foot by 2 foot cardboard plane, we would do a five-sided box without a roof, cut off the material in the corners, and tape that together to become the roof. Also, we decided that instead of using 4 bags and nesting each egg between 2 bags, our box could only fit 3 bags, and therefore we use 1 bag on the top to prevent ricocheting because we decided the bottom was more important. Finally, we also use bubble wrap. Instead of applying it directly to the egg, completely surrounding it, because the sleeves had to be reusable, we decided to create socks that the eggs could slide easily in and out of. And these are the reasons for these changes that I just went over. This is our final Mars lander vehicle in the flesh, and as you can see, it's just a box. Everything's on the inside, and it's really unassuming, but on the front you can see where the top opens and closes to easily be able to reach inside, grab the socks that the eggs are in, and take those eggs in and out of these socks. On the top page, on the top picture, you can kind of see how the cardboard roofing is makeshifted with the 4 corners that was excess material, and the side, there's not much to see.
So this is our lander vehicle test plan and results. This plan excludes the endurance test that we did at the end. And during both trials, we dropped the vehicle by 11 feet. So before each trial, we recorded the initial vehicle interrogation, and that was 0.6 feet by 0.6 feet by 0.6 feet, which is a box. And we began the timer and dropped the first box a height of 11 feet. And afterwards, we began the retrieval trial and recorded the vehicle interrogation, which was exactly the same. For a second trial, nothing else notable happened. We dropped the box 11 feet, retrieved the pilots, and for each trial, no recorded damage was seen for the pilots. However, the recorded load time is not available because we did not have enough team members at the moment to record load time. So here are our vehicle test results. The video on the left, which my assistant is going to play now, is going to be our first trial. And as you can see, I am the person on the right, and as I drop the box, it lands perfectly on its side. During the second trial, the results are the same. I drop the box, pilots are unscathed, and results are a success. Here's visual verification of damage to the pilots. As you can see, both LeBron and Zidane are undamaged and uninjured. And the vehicle integrity is completely the same. More visual verification of our optional endurance test, where we dropped it from around 26 feet, and our vehicle was undamaged and our pilots were kept the same.
So, what did we accomplish? In terms of design, our design was successful in keeping the pilots protected throughout the 2 main drops, as well as the additional drop from the 3rd floor. We were able to maximize the materials we could use based on budget, and we even had spare materials left over. Our design also showed no visible external damage and minimal damage internally, with some deflated airbags and the roof opening midway through our 3rd trial. So for the assembly, we followed the design procedure we proposed pretty much exactly. We maximized our time by keeping ourselves busy doing menial tasks, even when there was not any direct work that needed to be done. Because of this, we finished our design within the 30-minute limit provided, despite being one team member down. And in total, we do not believe that we could have used our time more efficiently. So this is our AI analysis, and it covers the test number, the drop height in meters, the impact time, the landing orientation, the vehicle damage, and the pilot condition. Some important things to note are that our landing orientation varied from upright to tilted to inverted, and that our vehicle damage went from 0 to 1 as our airbags deflated and the roof opened. So we used the Gemini 3 Flash free version to extract the data out of all 3 test videos, post-drop egg photos and post-drop box photos. This AI is limited in its abilities as the heights and impact times provided were slightly off, but still is impressive for a free model. Because it is difficult to convey all context to AI without confusion, AI systems are limited to non-perfect outputs that usually have to be constantly tweaked. However, the automation aspect is extremely helpful as data synthesis becomes more efficient, enabling for better rework or redesign decisions. Specifically, in our case, we could put more weight on the bottom to prevent the box from tipping, as shown in the table, because our orientation really varied in the trials. So for rework and redesign, while our design was able to pass the endurance test, the box completely opened midway through and the airbags were fairly deflated after the tests. Some potential options for redesign would include finding a better way to keep the design fastened, considering approaches to keeping the airbags inflated, and putting weight at the bottom of the box to prevent tipping.